Algebraic Topology, Understanding the Role of Topological Spaces. Algebraic topology is a fascinating branch of mathematics that combines the abstract world of algebra with the intuitive world of topology to study the properties of topological spaces. Within this field, homotopy groups and fundamental groups are essential concepts that help us understand how spaces can be transformed through continuous deformations. Fundamental groups. The fundamental group is the most basic type of homotopy group, providing crucial insights into the structure of a topological space. Denoted as pi_1 x_0, where x is a topological space and x_0 is a chosen base point. The fundamental group captures information about loops in X that start and end at x_0. Imagine all possible loops in X that begin and end at x_0. Two loops are considered equivalent if one can be continuously deformed into the other without leaving X. This process of continuous deformation is known as homotopy. The collection of these equivalence classes of loops forms a group under the operation of loop concatenation, joining two loops end to end. The constant loop at x_0 serves as the identity element of this group, and the inverse of a loop is simply the same loop traversed in the opposite direction. The fundamental group is powerful because it is a topological invariant, meaning it remains unchanged under homeomorphisms, continuous deformations that have continuous inverses. For instance, the fundamental group of a circle differs from that of a sphere, reflecting the fundamental differences in their topological properties. Homotopy groups. While the fundamental group focuses on loops, one-dimensional paths, homotopy groups generalize this concept to higher dimensions. The nth homotopy group, denoted PINX x_0, involves maps from an n-dimensional sphere to the space X that start and end at the base point x_0. Consider the second homotopy group pi_2 x_0, which deals with maps from a two-dimensional sphere, like the surface of a globe, into X with the image of a specific point on the sphere, often the North Pole, fixed at x_0. Two such maps are considered equivalent if one can be continuously deformed into the other while keeping the North Pole fixed at x_0. These equivalence classes form a group under an operation similar to loop concatenation. Higher homotopy groups PINX x_0 extend this idea to n-dimensional spheres. These groups allow us to study the structure of a topological space in progressively higher dimensions. Unlike the fundamental group, higher homotopy groups are abelian, commutative, for n2. Importance and applications. The study of fundamental and homotopy groups has profound implications in various areas of mathematics and theoretical physics. These groups provide a rigorous way to distinguish between different topological spaces that may appear similar but have fundamentally different properties. 1. Classifying spaces. Fundamental and homotopy groups help classify spaces up to homotopy equivalence. Spaces with the same homotopy groups are considered homotopy equivalent, meaning they can be deformed into each other through continuous transformations. 2. Covering spaces. The concept of covering spaces is closely related to the fundamental group. A covering space of a topological space X is a space that maps onto X in a way that locally resembles a direct product of X with a discrete set. The fundamental group plays a key role in classifying these covering spaces. 3. Obstruction theory. In algebraic topology, homotopy groups are used to determine whether certain types of maps or structures exist. For instance, given a map from one space to another, homotopy groups can help ascertain whether this map can be extended or lifted in a specific way. 4. Homotopy theory in physics. In theoretical physics, particularly in quantum field theory and string theory, homotopy groups are used to study the properties of spacetime and the possible configurations of fields and strings. For example, the concept of topological defects in field theory, such as vortices or monopoles, is closely related to non-trivial elements of homotopy groups. 5. Homotopy groups in modern mathematics. In contemporary mathematical research, homotopy groups are fundamental in homotopy theory, a central area of algebraic topology. They also play a crucial role in the study of fiber bundles, spectral sequences, and other advanced concepts. Examples. To illustrate these concepts, consider some classic examples. Circle, S circumflex 1. The fundamental group of a circle is isomorphic to the integers, z. This indicates that loops around a circle can be wound any number of times, positively or negatively. Sphere S squared, the fundamental group of a two-dimensional sphere, is trivial, consisting of just one element. This means any loop on the surface of a sphere can be continuously shrunk to a point without leaving the surface. Torus, T squared. The fundamental group of a torus, the surface of a donut, is isomorphic to z times z. This reflects the fact that a loop around a torus can traverse either of its two principal cycles independently. Conclusion. Fundamental and homotopy groups are powerful tools for probing the structure of topological spaces. By examining how these spaces can be continuously transformed, mathematicians gain deep insights into their intrinsic properties. The fundamental group, dealing with one-dimensional loops, and higher homotopy groups, dealing with n-dimensional spheres, together offer a comprehensive framework for understanding the complexities of topological spaces in both mathematics and physics. Through these concepts, algebraic topology bridges the gap between abstract algebra and geometric intuition, opening up a rich field of study that continues to evolve and find new applications.